is our technical speaker, Mohammad. Mohammad received a PhD degree from UMass Amherst in 2005, and he was a postdoctoral fellow at U Alberta from 2005 to 2008. He was a permanent researcher at Nuro, France from 2008 to 2013, and he was a recipient of the Nuro Award for Scientific Excellence in 2011 and obtained his habilitation in 2014. Since 2013, he has been a research scientist at Adobe, FAIR, Google, and now Amazon. He has published over 120 referred papers in major machine learning, AI, and control journals and conferences. He has co-chaired more than 10 workshops and tutorials at NeurIPS, ICML, and AAAI. His research has been mainly focused on the areas of reinforcement learning, bandit algorithms, and recommendation systems. Over the last 2 years, he has also been working on the problem of alignment in generative AI models. So, let's start.
So thank you for the introduction and for the invitation. Thanks for coming to the talk. So today I'm going to talk about the entropic risk optimization in discounted MDPs. It's a joint work with Professor Marek Petrick at University of New Hampshire and his student, and Professor Eric Delage at the Business School in University of Montreal. So this is the outline of the talk. I give you a preliminary just to open up about MDPs and risk measures. And then I'm going to talk about MDPs with two specific risk measures. One is the entropic risk measure, and the other one is the entropic value at risk objective functions. And then you're going to see the connection between these two risk measures and optimization with these two risk measures. I give you a little bit of numerical evaluation, and if you have time, I'm going to talk about risk-averse soft robust MDPs, which is a combination of both aleatoric and epistemic uncertainty. So in the most part of the talk, we just focus on the aleatoric uncertainty. There is this last part that if I have time, I'm going to very briefly talk about it, about how we can handle these two cases at the same time. So let's start with the preliminary. I know most of you are familiar with Markov decision processes and the risk-neutral MDPs, but just to establish the notation, I'll introduce that, and then I'll go to the risk measures and define what we mean by risk-averse MDPs in this part. So let's start with MDPs. So MDP, as you know, is a set of states and actions, S and A, reward function R, transition dynamic P, and initial state of the system S0, and a discount factor there. So MDP can be finite horizon or infinite horizon. So here I just say if t is less than infinity, we are talking about finite horizon, and t equal to infinity, we are talking about the infinite horizon. And as usually you know, for infinite horizon, we need to define the discount factor between 0 and 1, but for finite horizon, discount factor of 1 would be fine. And then you know that the policies, one of the general classes of policies, I didn't include the history-dependent policies in this slide, but one class of policies that is quite general is Markovian randomized policies. So in Markovian randomized policy, for each time step, you have a policy. So policy is a set of policy at each different time steps. And of course, we assume that can be randomized. And the equivalent for deterministic case is the pi MD, when we are still Markovian, but each policy is deterministic. And then if all these policies at different time steps are the same, then we are going to basically the stationary randomized or stationary deterministic case. So the reason that I put these definitions there is when you change the objective function from expectation to different risk measure, the first question is where the optimal policy is and which class of policies we should observe. So what we are interested, the random variable that we are interested here is the static risk measure, and the static risk measure on the return random variable. So return random variable is basically the sum of the rewards that you receive when you start from the initial state of the system and follow a policy. And we know because of the stochasticity, both in the policy and in the environment, every time you execute a policy, you're going to get a different sum of rewards. And this is the random variable that we are interested to control. So I put another term there because wherever you start and you continue that policy, you're going to get another sum of the rewards from that step to the end, and that one is basically a function of S. But what we are really interested in this math track R of horizon T and policy pi. So in the risk neutral, we just look at the mean of we are trying to find a policy that the mean of this return distribution is max. But for risk sensitive, we are looking at other objectives. Is it clear? So basically the random variable that we are looking at, this randomness, is this return random variable, which is the sum of the rewards. So let's start with risk neutral MDP that probably all of you are familiar with. In risk neutral MDP, as just I mentioned, what we are trying to do is, this is a random variable, has a distribution. I'm interested in the mean of this distribution. I find a policy that maximizes the mean. So the risk measure that we are using is expectation here. We know that for this class of policies, we've been studied this class of MDPs a lot. We know that the optimal policy in the finite horizon case belongs to the class of Markovian deterministic. So for every time step, you have a different policy. And for infinite horizon, the optimal policy is in the stationary deterministic. So you have one policy that you execute everywhere, right? So this is a known result. And as you know, the most important component in risk neutral MDPs, and basically whenever we work with MDPs, is the value function, which is the expectation of this return random variable. And we know that this expectation can be written using something we call Bellman equation. And using this Bellman equation, we write dynamic programming, and we can use value iteration or policy iteration to solve the dynamic programming. And all the RL algorithms are the sample-based version of either value iteration or policy iteration algorithm. The reason that we can write this nice Bellman equation, this connection, the recursive connection between the value function of one step and value function of the other step, are the nice properties of expectation. Because expectation supports the Tower property, the expectation of constant times the random variable is the constant expectation of the random variable. A lot of nice properties of expectation allows us to write these things in a very nice way and mathematically handle it. So we shouldn't take this for granted. This is the properties of expectation. As soon as you move away from this risk measure, things are not going to be as nice and beautiful as what we see for the risk neutral MDPs. Okay, so now let's go to risk measure. This part probably all of you are familiar so far, but let's start with the risk measure. So risk measure is a mapping from the space of random variables, and here the random variable of interest is that return random variable, to real numbers. And the very important class of risk measures are coherent risk measures. Coherent risk measure they respect four properties: monotonicity, translation invariance, sub or super additivity, depends on whether we are talking about reward or cost. You see the risk and the bad part of the distribution changes, right? So in one case, we talk about sub additivity. In one case, we talk about super additivity. And positive homogeneity. This positive homogeneity I emphasize a lot because later when we go to entropic risk measure, this is a property that plays a very important role. And this basically means that if you apply a risk measure to a multiplication of a positive constant and a random variable, you can take that positive constant out and apply the risk measure to the random variable. So this property is called positive homogeneity. And if all these properties is satisfied, then the risk measure is coherent. Now, what is convex or concave risk measure? Here I'm using convex and concave in a kind of interchangeable way because depends on whether you are doing reward or you're doing cost, you move from concavity and convexity. So since we are working with reward here, everything is concave, but I abuse the word and I say convex here. So just convex and concave basically is just the equivalent property for these two cases. So the convex risk measure basically satisfies monotonicity and translation invariance, but replaces sub or super additivity and positive homogeneity with what we call it convexity or concavity. And it's very clear that every coherent risk measure is convex, but not the other way around. Okay, so these are very important properties of risk measure. Let's start with some of the popular risk measures that probably you have seen. The first one is value at risk or VAR. So value at risk at level alpha, and alpha is a number between 0 and 1, is basically 1 minus alpha quantile of the random variable, or basically the worst 1 minus alpha quantile of x. So for example, the value at risk at level 0.9 for a distribution that represents the return, we are talking about reward here, is basically 10% tail of basically left tail of that distribution. If you go to cost, then everything, the bad tail goes the other way, right? So the point that cuts the CDF of the distribution and between 90% and 10% is the value at risk. And you can see that one of the problems is if there is a discontinuity in the distribution, this value at risk is not unique. And this is why, despite its very nice meanings, it's not very nice to work with because of discontinuous problems. And it's not a coherent risk measure. The other popular risk measure is conditional value at risk, or CVAR. CVAR basically says, okay, we define VAR, we look at that bad tail. If I renormalize that bad tail, that 10% of the thing to 1, and then find expectation, that places the CVAR. So CVAR is the expectation of the 1 minus alpha, worst minus alpha fraction, right? So just cut the distribution, look at that bad tail, calculate its expectation. That's what we call CVAR. And CVAR is a coherent risk measure, unlike VAR. And you can easily see that if alpha is equal to 0, then that bad tail becomes the whole distribution. So CVAR is basically expectation. So it's very simple to see. And then the other limit of it is essentially infimum, which will, yes.
Just to connect it to more practical, like online sorts of, let's say, reinforcement learning, it is like running the policy and observing the return.
Yes.
Right? And then those are our samples, and then we can now.
Those samples follow a distribution.
Yes, yeah. So those are random variables which are taking different, like amount every time.
So every time you run a policy, you get a sum of rewards.
Yeah.
You repeat this process, you get a bunch of numbers. These numbers follow a distribution. That distribution is the distribution that we are talking about. Yeah. And that random variable is the random variable that we normally work with this expectation in the risk neutral case. But when we go to risk averse, which I'm going to define, we are going to look at the, so there is a question. So that doesn't matter for single dimensional or multi-dimensional variable. This is the distribution. The distribution can be multivariable or can be single variable, doesn't matter. The case, but the return is actually, no, I take it back. Return is a scalar. Return is just the sum of the rewards. If you go to multi-objectivity, then maybe the multi-variable becomes a case. But here, return is a scalar. So we are not talking about the multivariable distributions. Just the question that was posted on the chat. Okay, but these are the two popular ones. The one that we are looking at today is entropic risk measure. Entropic risk measure, this is the definition of entropic risk measure at risk parameter beta. There is a difference between this beta and the risk level alpha in the previous slide. Alpha in the previous slide was a number between 0 and 1. Beta here is just a positive number. So this parameter doesn't have any connection to alpha. So these are some properties of ERM. So as you can see, if beta goes to 0, ERM coincides with expectation. The second case basically is a very good definition of what this ERM risk measure means. So in the Gaussian case, ERM coincides with mean variance risk measure, which is a very popular risk measure that was studied back in 50s in finance. But for non-Gaussian distribution, there is an extra order of beta term there. So just to connect what this risk measure means, think about it as some representation of mean and variance of that distribution. And then the third property basically shows that ERM is not positively homogeneous. Because if you have a constant, you cannot take it out. Therefore, it's not a coherent risk measure, but it's a convex risk measure. And we're going to see that this is going to cause problem when we start working with this risk measure. And then the third one is the tower property. It has the tower property. So this is nice. So you remember when I told you Bellman equations is because of nice properties of expectation. These nice properties is tower property, positive homogeneity. And this one has one of them, doesn't have the other. So it's not a coherent, but it's a convex risk measure. The other risk measure that is relatively new is called entropic value at risk. It defines at confidence level alpha. So if the risk level of this is interpretable with C bar and var. See, this is between 0 and 1, and it's defined based on the entropic risk measure. So in order, again, to get a sense of what this risk measure means, this risk measure is a very tight lower bound of C bar. Right? So this basically means that then why people basically picked this risk measure and started working with it is because it has connection with C bar. How tight this is questionable. I don't think we have very good understanding for all distributions how tight this lower bound is, but you can think of E bar as a reasonable surrogate for C bar and bar. So this is why people started studying this risk measure. Okay? It's a coherent risk measure, so it's good, like C bar. And as you can see, again, at the limit, it becomes expectation.
Is coherence the only reason for preparing this one, or are there
The connection with C bar is, and now people are finding out that maybe even computation that working with this is easier. It's not easy
compared to C bar.
But we are going to show that there are ways of dealing with this risk measure. Still, C bar also has this, because C bar also has its own problem. But right now, the reason that people are looking at it is more as a surrogate to conditional value at risk. But as I said, how tight this bound is depends on the distribution. I'm not aware of something that works over all possible distributions, but for many practical distributions, is a tight bound. Okay. So now let's see, so far we talked about risk measure, we never talked about what is risk-averse MDP. Risk-averse MDP is when we are replacing expectation with a risk measure. We just say, okay, I'm not optimizing for expectation, I'm just optimizing for risk measure, but the random variable is still the return. Instead of finding a policy that maximizes the expectation of this return random variable, I find a policy that maximizes the risk measure of this return random variable. There are also studies on a combination of mean and risk measures. Some people are looking for policies that maximizes mean subject to a risk measure being bounded by something. These are different kinds of risk measures. Here we simplify it, you're just maximizing the risk measure. Okay. And as you can see, all the randomness is coming from return, and all depends on the randomness in dynamics. So it's an aleatoric uncertainty, right? So it's all coming from the uncertainty in the system. Okay.
So just one question: when we maximize basically this risk averse, so is there any connection to maximizing the expectation also?
No, it depends on the risk measure, because as I said, expectation is also a risk measure, right?
Yes.
But if you're looking at the tail of the distribution, you're basically seeing that I'm putting the bad tail
Okay.
the right side, or in the cost case, I'm minimizing. So I'm pushing the bad tail, which is now the right tail towards zero. So that's you can look at it. Of course, this is the kind of extreme case that we only focus on the risk measure. As I said, there are in practice people are mixing expectation and risk measures, and then it becomes like a different form. But here is just okay. So now, just for those of you who are maybe have seen the nested risk measure, there are some other concepts. It's called nested risk measure or nested C bar. So nested C bar is a specific form of CVAR that is not a static risk measure. The risk measure is not applied to the entire return random variable. It applies in a kind of step-by-step way, meaning that you apply the first CVAR to the first reward, and then another CVAR to the reward from that point on, and the CVAR point on. So this is a different risk measure. It's called, and it can be applied to other risk measures, not just for CVAR. I wrote the equation just for CVAR. If you define the risk measure this way, that you can easily break down this return, which is the sum of the rewards, this way, then you can write the dynamic program. So why this nested risk measure is popular? Because you can write easily the dynamic program, because it has all the nice properties that expectation has. But this is not the static risk measure. It's more, they call it nested, iterated, Markov. There are different ways of defining this. And as I said, the favorable properties is the computational property, because then you can write everything like expectation as a dynamic program and Bellman equation. The bad thing is it can be a very, very poor approximation of the static risk measure. For example, if you look at there, the blue is the CVAR of the return. The green is the nested CVAR of the return at different confidence levels. So this has, if your goal is just to look at the entire return and look at the randomness of that, this could be a very bad surrogate. So it's a trade-off. Mathematically, it's easy to deal with. In some problems, it's not that far away from the static CVAR, but in some problem can be, this is a kind of a synthetic problem. It can be very far away. So it's again a trade-off between computation and other. And the orange graph that you see is EVAR. I told you EVAR is a lower bound of CVAR. In this particular problem, it's a very, very tight lower bound. Right? So this is kind of justifying why EVAR is used and why nested CVAR is not. But there are different problems. You see different relationship between these quantities. So now, let's go to this Tower property and positive homogeneity. These are two very important properties for writing Bellman equation. Expectation and nested CVAR and minimization. Minimization, for those of you who are familiar with min, max, or robust problems, mean also plays a role. But forget about mean. Expectation and nested CVAR, they have both properties, and this is why you can write a very nice Bellman equation for them. But the others, like ERM, CVAR, and EVAR, they either have the Tower property or they have the positive homogeneity. Therefore, you cannot write a very nice Bellman equation for them and solve them. Right? So that's just a summary of these properties. So now let's focus on MDPs with ARM objectives. So far, everything was just introductory. So now that you understand what is the risk-averse MDP, now let's focus on a risk-averse MDP when the risk measure is this entropic risk measure and see how we can solve this MDP. Okay, so discounted MDPs with ERM objective. I emphasize this is discounted because it's been some work on average reward MDPs with ERM. This is specific for discounting. Okay, so what is here? You are trying to maximize, find a policy such that the ERM at parameter beta of the return random variable is maximized. Right now, I put the history-dependent randomized policies because I don't know where the optimal policy is, so I put the most general form. But I show you that the optimal policy is actually in a very smaller class. It doesn't have to, you don't have to look at the history-dependent randomized policies. Here, just to show you that if you want to write a Bellman equation for ERM, so you apply ERM, so imagine that the horizon is 2, so return at the 2 step is R at the step 1 plus gamma R at step 2. So if you apply the ERM, you send the ERM in, but the third step is broken because you cannot take the gamma out. Remember, ERM was not positively homogeneous. So you cannot take the gamma out. So if you could take the gamma out, so when you send it in, you're using the Tower property. Expectation has the Tower property. ERM has the Tower property. So the first line, the first thing is kosher, is clean. The second one is not, because you're taking now a constant out, but ERM doesn't have that property. If you could have done this, then you could have written the ERM as this. You're going to have the Bellman equation. You could apply the same algorithms that you are familiar with for risk neutral to this, but you can't. Okay, so it's coming from the lack of this property. So now let's see how we can handle this. So the first result that we have here that allows us to do something is we call it positive quasi-homogeneity. It's true that when we apply ERM to a multiplication of a constant and a random variable, we cannot take that constant out, but we can take that constant out if we change the risk parameter. So if we had the positive homogeneity, ERM of Cx was C ERM of x. But here, ERM of Cx is C ERM of x with a different risk parameter multiplied by C. So what does that mean? If the C is the discount factor, means that the value function at each time t is the ERM of a random variable with a risk parameter that is time dependent. So one thing that is very important is as t gets larger, gamma to the power of t goes to 0, and ERM of 0 is expectation. So if the horizon gets larger and larger, at some point ERM coincides with expectation. But before that, you have to consider that if we had the nice property, you didn't need this time-dependent risk parameter, but we don't have it. We had the quasi-homogeneity. So now we can write the value function this way. Okay? And calculate the optimal policy. And this is also, remember, we're going to use this fact that when t goes to infinity, gamma to the power of t goes to 0, and then ERM coincides with expectation. So at some point, we don't need to be worried about the risk. Okay? So this is one. The second result that we are using here is we can write the Bellman equation. Now we write the Bellman equation. But the Bellman equation is time dependent. The risk parameter is time dependent. Right? So it's changing. Your risk level or risk parameter keeps changing as t progress. Okay? And then you can define also the optimal value function the same. Okay? So if you solve the kind of, for those of you who are familiar with finite horizon MDPs, you basically start from the end and do the backward things and come back. Now, when you do backward, instead of having just one fixed risk measure here, like for example in expectation, you have a fixed expectation here. Here, this risk measure keeps changing with time. Okay? And then now here we prove that, remember when I emphasized that when you change the objective function from expectation to something else, the first question is where is the optimal policy? Here we can show that the optimal policy belongs to the class of Markovian deterministic policies. So if you calculate the optimal value function, then you can extract the optimal policy. So it's deterministic, it's randomized, but you don't need to bring any history to the things, because some of these the risk measures, the optimal policy is history dependent. Here you don't need any history. Okay. So now you saw that, remember again, go back to expectation. So you needed three pieces. And first you needed dynamic programming, then you needed the formulation for optimal value function, and then you needed the formulation to extract the optimal policy from the optimal value function. When you had all of them, you could apply your dynamic programming algorithm and calculate the solution of the MDP. Here, we have all the pieces ready. The optimal value function is coming from equation 2. The optimal policy is coming from equation 3. So you have all the pieces for doing dynamic programming. The only difference is your risk measure now changes with time, instead of a fixed expectation that you had there. Yes?
Would that cause any problem for model-free case? Like if you're just sampling for, building these estimates? Because, like when we sample, those risk parameters are I don't know how we get those per, TD sort of.
That can cause some problem, but that's not the main. That's not the main difficulty.
Okay.
I think the main difficulty is we haven't extended this to functional approximation, but I think with these results, there's a possibility to extend that. Everything here now we are talking about everything tabular case. You can do dynamic programming. I think that can be handled, but I need to think more about extension to functional approximation and the sample-based case.
That's a quick
Mhm.
question. We can have a tabular case, but we don't know the dynamics, right? So we will end up sampling.
Yes, that here we assume that the dynamic is known.
Okay, all right.
Yeah, if it's sampling, you just one way of it is just replace expectation with sample and hope for the best. That's the simplest case.
But what do we do with the varying risk parameter in those?
So here, if you look at the next state, you can
There is a way to
sampling, but it's how accurate and how much you lose. I don't have a clear answer. But by sampling, you can look at multiple next states and build the distribution and apply the ERM to that distribution. So that's possible. And there are actually algorithms for handling this out there. But then you lose how much you lose, I cannot bound. The implementation is doable. So now, let's go to the algorithms for this case. As I said, we have the main components. We have the optimal value function. We have how to extract optimal policy. So we should be able to do a value iteration here. So for finite horizon, things is very simple. You just initialize the value function at horizon capital T, and you do the backward and calculate V using the equation 2, which is this equation that you saw, this one, and then extract the policy using equation 3, which is this equation. So with these two, you can easily apply a backward dynamic programming and calculate the optimal policy and the value function. Again, tabular and dynamic node. Sample-based has its own issues, and how you implement it, we may lose differently, but this is the case. But this is finite horizon, and you may ask the question that if it's finite horizon, then discounting doesn't have that much sense in finite horizon. So now I use this to define an infinite horizon algorithm. Yes?
So we can calculate this in closed form because we have known dynamics and the tabular discrete states.
Yes.
Okay, if it's continuous state, we need to go to
approximation. There are some approximations out there, but most of them are defined in an average reward case. So it's going to be it's a possibility, but we don't have any. We have recipes for extending it, but I don't have any good idea how much we use and how to bound it. So now for infinite horizon, I use the fact that if T is large, ERM with beta times gamma to the power of T becomes expectation. So what I do is I choose a pseudo horizon T prime. I solve the risk neutral MDP and initialize my V star and pi star at horizon T prime using the solutions of the risk neutral MDP. Remember, if T is large enough, risk becomes expectation. So solve the expectation one, the risk neutral one, initialize the value function and policy at horizon T prime using those, and then do the backfit. So this is very simple idea. So now the main question is how large this T prime should be. And this is how we can bound it. So the difference between the solution of the original infinite horizon ERM minus the solution that we return is less than C times gamma to the power 2T prime. So C is related to gamma as 1 over 1 minus gamma squared, and delta R is the range of your reward. Beta is the risk parameter, and T prime is this. So basically, the larger you choose the T prime, you lose less, which is obvious. It's not very, so the smaller T prime you choose, you will reduce your computation because that backward process becomes simpler or shorter, but you lose more. This is obvious. And now, just to show you, here in the algorithm, we set initialize the value function at horizon T prime with the solution of the risk neutral. If you don't do that and you just initialize it arbitrary, you get the same bound, except instead of the gamma to the power of 2t prime, you get gamma power of t prime. So you lose a power of 2. So by just a smart initialization, you gain a power of 2 there. So again, nothing is for free. You solve an MDP extra, but you gain a power of 2 here. And then this is also another way of writing this. If I tell you I want delta optimality, your algorithm runs in this time. So this is the complexity of the algorithm. So if I ask you, go for delta optimal things, meaning that the right-hand side is delta, then you need to this much computation. Okay? So this is complete formulation of ERM MDPs in the discounted MDPs, where the optimal policy is, how to write the Bellman equation, how to write the value function. The only thing that is interesting here is the risk measure is time dependent. And we have an algorithm, this dynamic programming algorithms to solve. And we know that even for RL, before doing RL, we need to have a dynamic programming algorithm, and then we go for the sample-based version and develop RL. Okay, so now let's go to EVAR and see what is EVAR, because maybe you are not happy with mean and variance form of risk measure. You are more caring about the tail of the distribution. So as you can see, the ERM is related to mean and variance. For those people who are interested in the tail, they are interested in VAR and CVAR. So now we propose EVAR as a surrogate for VAR and CVAR. So let's see how we can solve the EVAR. So again, the optimization problem, the objective function is finding a policy such that the EVAR at risk level alpha of the return is maximized. I just repeat the properties of EVAR. EVAR is coherent, is interpretable. Why is interpretable? Because its alpha is related to the alpha of CVAR and VAR, and it's a lower bound for CVAR, but it doesn't have the tau property. So again, because of this, you cannot write the Bellman equations easily. Because when I wrote that simple example, I showed you, you need Tower property, you need the positive homogeneity. This guy has positive homogeneity, doesn't have the Tower property. Okay, so now we try to solve this by connecting it to ERM. Let's first start with the definition. The first line is the definition of EVAR. So EVAR is a soup over beta of the ERM plus a term that depends on the risk parameters of the ERM and the risk parameter of EVAR. So now, when you look at the objective, you are maximizing the EVAR. If I maximize the EVAR and we can switch the soup and max, which is possible in this case, this has some technicality, then you have the max over ERM and a term that is independent of policy. So look at this equation. Max is applied to ERM on the right-hand side and a term that is independent of the policy. So because of this, we can very easily say that if pi star is an optimal solution of EVAR, then there exists a risk level beta star such that the pi star is also optimal for the ERM MDP at beta equal to beta star. Why? Because here this max is over the ERM, so there is a beta that the optimal policy of these two coincides. Okay. So the first thing that this tells me is where was the optimal policy of ERM? Optimal policy of ERM was Markovian deterministic. So this immediately tells me that there exists an optimal Markov deterministic policy for EVAR as well. So this tells me that where the optimal policy of EVAR MDP is. So this is good. It's good news. We don't need history. We don't need anything. A deterministic Markovian policy handles the EVAR. Okay? So now let's see how we can come up with an algorithm. So I repeat the same equation. The max of EVAR is the sup over beta max of ERM. The problem is, unlike the EVAR objective, this term, because of the max, this term is not concave. Everything from max on is not concave. So therefore, we cannot just apply a gradient on beta and go for the minimum of beta. So optimizing over beta is not easy because the objective after the supremum is not concave or anything because of the max over the policy. So this makes the life hard for us, right? Because otherwise you could do two optimization. You could do an inner optimization, which was an ERM optimization, and then you could basically have a gradient applying to beta and make beta go to the optimal. That is not possible. So the best solution we have so far, of course, you may come up with something smarter, I don't know. The best solution we have is discretizing beta. So we just discretize beta at k levels, and for each level we solve the ERM, and then we calculate among all these solutions, we pick the best using this k star, right? So this means that for solving EVAR, you need to solve a sequence of ERM MDPs. Okay. So now the question is, what can we say about the quality of this solution, how this discretization plays a role? We have some results that basically gives a very specific form of discretization. If you discretize according to the recipe that you see in this theorem, then you can show that with this much computation, you get a delta optimal policy for EVAR. This computation is heavy because, as you can see, what is the killer here is 1 over delta squared. So if you want to be very close, then the computation grows with that. Right? So that's, but this is a kind of like way of working. So we have done a few improvements here. So one thing that helps us with computation is when you solve each ERM MDP, you are doing ERM at level at risk parameter beta. But when you're solving ERM at risk level beta, you solve beta gamma square, beta gamma cube, and so on and so forth. So you calculate the value of ERM for multiple betas. So if you are a little bit careful, you can keep those results and reduce amount of your computation because you get the value function at all those levels. And then we have also a branch and bound algorithm for this, which we haven't published it, and that helps also a lot in terms of improving the complexity. But in any case, the whole complexity is coming from the fact that we need to discretize over beta. We don't have any optimization that we solve the inner product and then take the gradient of beta and move. This is an open. If we can do something there that helps with the complexity, but this is what we have so far. So let's do some numerical, look at some numerical evaluation. So I just give you the setup. So in all these experiments, what we are optimizing is the EVAR at parameter 0.9. So alpha is 0.9. So we are looking at the 10% bad tail. And we consider the horizon of 100. The reason I consider horizon 100 because I want to calculate the optimal policy, because these are simple problems. And I do the evaluation by running 100,000 episodes of size 100 to have the truth. So basically, the reason that I consider finite horizon is because I want to have the truth. And truth, we calculated basically Monte Carlo with 100,000 steps. And the algorithm that we want to show is EVAR. I'm not trying to, because if my EVAR algorithm performs reasonable, this means that my ERM algorithm also performs reasonable, because the heart of the EVAR algorithm is my ERM algorithm. We're solving the sequence of ERMs. So I did we have two goals in our experiments. The first one is ablation study. So we made a couple of decisions, and we want to see whether these decisions were helpful or not. One of them is we did this grid. I gave you a recipe for the grid. If you remember from this theorem, I gave a recipe for the grid, and I managed to bound it. I just want to see that whether this recipe, other than helping us to bound the result, has some practical implication, or if I just if I just put a uniform grid, I'm going to get similar results. So the first ablation study is do the algorithm with uniform grid instead of that recipe. The other one is, you remember when we did ERM MDP, we told you that ERM changes time dependent. If I just ignore that the risk level changes with time, I just write the Bellman equation the way that I write it for expectation, and I apply it to that. So this is you're basically not optimizing the ERM. You're just optimizing something and see what happens. And then the second part of the experiment is comparing to a bunch of baselines. So of course, one baseline is you give me a risk sensitive problem. I just pretend that I didn't hear you. I solve the risk neutral MDP. So that's one case. The other case is this nested problems. As I told you, the nested has these nice properties that has Bellman equation and stuff, but could be far away. So nested C-bar and nested E-bar. And the other one is just, I just solved the ERM and hope that ERM gives me a good result for E-bar. And then another baseline that I'm using is an algorithm by Yilnam Chu, Marco Pavoni, Shai Manor, and Aviv Tomar back in 2015, which is an algorithm for solving C-bar, but it augments the state space. And actually, we showed last year at Nuro that the algorithm is incorrect. But that algorithm is not correct, but not correctness is pretty technical. So for some problems, it actually works, for some problems, it doesn't. So we also try to check it with that. And this is a very heavy algorithm because it's look at the history-dependent policies. It doesn't look at the Markov policies. It tries to find the history-dependent policy for C-bar. So these are the competitors that we looked. The first set of results are, the problems that we looked are very simple problems because all the results we have is tabular problems, right? So we look at these problems. These are standard in OR and machine learning communities. One of them is machine replacement, the other one is gambler, the other one is inventory management, and the other one is rear swim. So these are examples that are common. And then we have done our comparison. So whatever I show boldface in this table is when the results is in the 95 confidence interval of the optimal solution. Remember, I can compute the optimal solution with Monte Carlo, so I do that there. So here you can see our algorithm actually performs the best for all the problem, but there are a couple of observations here. The naive grid in 4 out of 5 problems performs very similar to us. So this ablation study shows that the choice of that grid, which was important for us to show some theorem to you, may not be that important in practice. Because if I just do naively uniform grid, I'm getting more or less the same solution. But if I pretend that ERM doesn't change with time, then I'm going to lose big time. So naive level is not going to work. And that's very obvious because, as I said, you're just pretending an operator has a property that it doesn't, and it's not working. So that's good. And then the other results, you see that nested C-bar and nested E-bar actually didn't work very well. So for all these problems, when you go for nested, you're losing big time in terms of the static risk measure. And the risk neutral surprisingly worked well for 3 out of these 5 problems. This basically shows that the risk sensitivity in these problems is not that much. Maybe if we change the risk level, we see the difference more. But with level 10% or 0.9, we don't see that much difference. So this is this. Then the previous table was in terms of the E-bar. This table is in terms of the C-bar. If you remember, we are doing E-bar because E-bar is a surrogate for C-bar. So our algorithm solves EVAR with the hope that it's a good surrogate for CVAR. And as you can see, again, our algorithm for 4 out of 5 problems is within the optimal. For the one of the problems is not. So this problem probably is a problem in which the gap between the CVAR and EVAR is large. Again, we see the effect of greed is not that much. So it seems that if you're worried about following that instruction of building the grid, you can ignore it and do the uniform grid. But the naive level is still important. So if you just pretend that ERM doesn't change with time, you're going to lose. And here you see even the augmented CVAR is only good for 2 of the problems, although this is solving for CVAR with a history-dependent policy. And this comes from the fact that, from 2 facts. One, we restricted the time of the algorithm. This algorithm is very expensive. And the other one is that bug in this algorithm. So these are the comparison. This is the time of these algorithms. As you can see, this augmented CVAR is extremely expensive. So because it's looking at history dependent. Our algorithm solving the ERM actually is very cheap. The solving ERM is as expensive as solving a nested CVAR. Why? The reason that our algorithm is more expensive than many of them is because we have to solve a sequence of ERM problems. So that how many ERM problems we solve make this expensive. So if we can kind of reuse some of those results or using that branch and bound, which we haven't tried it in these experiments, we might be able to get better results because ERM is solving quickly. Right? So this is the time dependency. So just to summarize, we basically showed you the first exact dynamic for programming formulation for ERM in discounted MDPs. We showed that the optimal value function exists. Optimal policy is time-dependent and deterministic. So, and we propose a value iteration algorithm to solve this problem both in finite and infinite horizon. So if you want to go to function approximation, this could be a starting point and see how we can extend that. For EVAR MDP, we approximately optimize it by reducing it to multiple ERM MDPs. And we empirically showed the results that this could be a good surrogate for CVAR and can be solved properly. So if I have time, if I can give you a little bit more about this epistemic aleatoric MDPs, but if I prefer to stop here and if you have any questions, you ask. If I have time, I go to the other, because the other one is like a bonus part and it's a little bit orthogonal to the discussion. Any question about the risk measure and the lessons? Basically, the lessons are, as soon as we go to risk measures, nice properties that we are familiar with in expectation is broken. And because of that, we cannot write the algorithm in a dynamic programming form and use all the tools that we are very familiar with, this value iteration algorithm, to solve it. And always with risk measure, there is this trade-off between computation and how much this risk measure really captures the static risk in the return random variable. For example, CVAR is not, nested CVAR, which is nice computationally, doesn't capture the randomness in the static form of the return. So there is basically a trade-off here. And I think I made it clear to you that why EVAR and ERM are good. ERM is good because, as you can see, the computationally is nice. Still has some tricks, but still is computationally nice. And EVAR is important because is a good surrogate for CVAR, and we are trying to see whether we can have algorithms for EVAR that are simpler than CVAR. If it's not, then probably people are going to look at CVAR because it's more relevant. Any question, please ask.
So basically, we talk about, so the problem about the second method was that you should, it's non-convex. So I want to know if you do any research about, I mean, that the shape of this non-convexity over beta when we change that.
We have actually some graphs in the paper. We show that it's not concave. It's concave, it should be concave. And it's not, unfortunately. But it might have some properties that either we missed or someone with better understanding of optimization can capture it. I don't know. But unfortunately, if you have actually, I should have put it on the slides, but we have it in the paper that we show that the optimization is not convex, concave. Yep.
Yeah, this is a slightly more general question. So I know, we have risk-averse RL and we have safe RL. They are different because they optimize for different objectives, but they are related in a way. They each of these approaches, they try to manage some form of risk, right?
Depends on the form of constraint or safety
Yeah.
that you define. Yes.
Yeah, okay. So I like to think, okay, when I have a problem, is this a correct statement? Like if the aleatoric uncertainty is large in a problem, we might be leaning toward risk averse. But if, for example, in robotics, I'm inclined more to use a safe RL approach. But in gambling or problems that involve high risk, sort of like or high uncertainty, it looks like risk averse might be a better.
I can tell you that there are a lot of results that connect robust MDPs with risk. So it depends on how you define the feasibility set for the robust problem. You might find an equivalent for risk. Constraint, if you define that as a constraint, then there is a connection. But constraint is much more general than the return, right? For example, because return is everything depends on the dynamic of the system. But constraint, I can tell you that, there is a wall, for example, and you're not supposed to hit the wall. Or there is a part of the environment that you're not supposed to go there. Or even if you go there, you're not supposed to stay there for longer than something. Think about, I don't know, the temperature. If your temperature goes above something, you can survive. But if you stay, I don't know, more than some, then the system is going to blow up. So there are forms of constraint and safety that I don't know how to translate them to risk. But connection between risk and robustness is easier to understand. Basically, the relationship between the way that you define the feasibility set of your robust problem and the risk measure. There are some connections between these two.
Got it. Just a quick add-on. Have you seen any of risk-averse approaches applied to robotics, for example? Like strictly robotics, not just control.
So this person he was at Caltech. He's no longer there. I think he joined the startup. Ahmadi. He actually has done a lot of robotics problem with nested EVAR. And as I said, the reason that people go for this nested risk measure is because it's easy to implement. And he has done some work in this area. There is another guy, Ahmadi something, and that guy has worked in definition of EVAR. He did his PhD in Russia. This is not that guy. This guy is a graduate from MIT, and he was doing a postdoc at Caltech. So this guy has applied nested EVAR to robotics. I don't know exactly the applications, but. And also that connection between robust and risk, robustness has been used in robotics, certain degrees. But anyway, I think I skipped the last part but that part, there are ways of combining and addressing the two risk measures. Basically, when you have risk over the epistemic, which is related to robust formulation, and the aleatoric, which is related to to risk. It's a combination of risk and robustness. We can do some stuff there, but we are at the very preliminary stages. Any other question?
Let us thank the speaker.
Thank you very much.